Welcome, everyone, and thank you for joining us today for our webinar titled An Insider's Guide, Tips and Tricks to Get the Most from Graph Data Science in the Enterprise. My name is Meryl Lee, and I'm part of the webinar team here at Neo4j, and I'm joined by Dr. Alicia Frame and Amy Hodler. A few housekeeping items before we get started. We invite you to submit any questions you have throughout the session using the Questions tab located at the top of your screen. We're hoping to be able to answer questions from the audience at the end of the discussion, but if by chance we don't get to yours, you can always email them to webinar@neo4j.com. I also want to let you know that this webinar is being recorded. With that, I'll hand it over to Alicia and Amy.
Thank you so much for that awesome introduction. Amy and I are super excited today to be talking to you guys about what we're calling the Insider's Guide, but I think of it as like all the really cool stuff in GDS that's not the algorithms. And so really, how do you get that last mile performance out? What are the tips and tricks that only GDS pros know? So we're going to cover a couple different topics today, going from memory management. So how do you configure Neo4j to run GDS? What do we have built in to better handle your memory when you're running your algorithms? We're going to talk about transforming your graph and all of the cool stuff with the graph catalog that lets you reshape your transactional database to the right subset or flavor of data that you want to run algorithms on. We'll be talking about the new RBAC integration or fine-grained security that we just rolled out in GDS 1.3. We'll talk through algorithm tuning, so all of the different parameters. So when you call, GDS.PageRank, there's a whole lot of different things you can tweak and change, and what do those mean, and what do you do with them? We'll talk about graph versioning with graph export. So once you've done your work, how can you save a snapshot in time? We'll explain the tiers of algorithms and the alpha tier for early access to new features with a sneak peek of some embeddings. And then we'll end up with talking about running your own algorithms, writing your own algorithms using the Priggle API in Java. And with that, I'm going to pass it to Amy.
Great. Thank you, Alicia. We've got really cool things to show you. But first, a little bit of background, especially if we have people on that aren't as familiar with the library. If you're not, get it, play with it. It's a lot of fun. But if you're wondering, why would I use graphs with machine learning or for analytics in the first place? The very easy answer is you can get better predictions with the data you already have. So if you have small data, or you just want to improve your predictions, and who doesn't, graphs can help you do that. And so we hear this a lot from data scientists that, hey, if I just had more data, I could improve my predictive lift. But the thing is, you already have more data. It's called relationships, and it's hiding in your data sets already. So a lot of current data science models kind of ignore the topology of the network, the structure of your data. And so adding that in can just add in and boost what you're already doing. You can add in very predictive features to your machine learning models, and whatever forecasting you might be doing. And some of these analytics actually help you make predictions that you otherwise couldn't, or answer questions that you otherwise couldn't, because you're not actually using the relationships. One important thing to say is that we're not asking you to throw out what you're already doing. The nice thing about graphs and in particular graph feature engineering is you can add it to your current pipeline. So keep doing what you're doing, but add in those relationships as well. So the other quick thing is we're talking about graph data science. Neo4j has a graph data science bundle that serves the purpose to help you get up and going quickly. It consists of 3 different elements: the Neo4j database, so you can create your graph somewhere, save your graph somewhere, and you can persist any results that you might find using the data science. The data science library itself includes algorithms and an analytics workspace. And we've also included Bloom, which is the Neo4j exploration tool, a visual exploration tool. What we found is that data scientists may love the numbers. They like nothing better than a vector, but they may love the numbers, but they have to also be able to intuit what they mean and explain them to their line of business or their subject matter experts. So we've packaged all this together so that people can have kind of the complete tool set of what you need to do the graph data science itself. We're going to be talking a lot about the library today. I actually think all about the library today. So what's in it? There's over 50 graph algorithms in it. They range from pathfinding, centrality, community detection, to things like link prediction and similarity, where you're doing a more set comparison. And we've just added, and we'll talk a little bit about this, some graph embeddings as well. So lots of algorithms that help you kind of understand the topology and compute metrics on that. And they're very parallelized so that we are able to perform and scale to tens of billions of nodes. So we're very proud of being able to get to that level of scale in production. Those algorithms compute and work in a computational graph space. So I'm quite impressed with what the team did here, is to take something that was stored very efficiently. So Neo4j has a native graph storage that is very compact, works really great for storage and traversals, but not as great for computation. So what they've done is actually have this automatic transformation into from a transactional graph into a computational graph that is very efficient for these large global traversals, which graph analytics tend to touch a lot of area of your graph. So being able to be optimized for that, and then it's also in memory, and we'll talk a little more about that too, but that allows you to do things like reshape your graph while it's in memory, to layer on different graph algorithms, and then save out your results when you're ready, or export them to a new graph. So that's what's in the library itself. If you've played with the library, but you haven't looked at it in the last couple months, you haven't upgraded, you definitely should upgrade to the latest version. Since the initial release, we've added many new algorithms. We've also optimized many of the algorithms that existed previously. We've also added in new features such as seeding for more consistency. We've added in statistics. We've added in community ideas. So a lot of features as well. We'll dive a little deeper in some of those in a minute. We've also added in more expressive and features that allow for higher performance of the in-memory graph. So I mentioned the in-memory graph and reshaping already, and then also the things like the ability to export to a completely new database as well. We've also done things for the graph loaders to speed those up. And again, just making the in-memory store as compact as possible so that it will perform better. Finally, some just general advanced features that we've added. Those include things like support for role-based access security and support for Neo4j 4 and 4.1. We've also added some memory estimation, so the memory management, and you can act as kind of a guardrail for what you may be running. And we've added the Pregel API for implementing your own algorithms. So that is the super fast summary of what's been added recently. Alicia, anything to add on the most recent stuff?
No, that was a really good overview, and we'll definitely touch on some of those things in depth in the upcoming demos, so get excited.
Okay, great. So now the fun part, and you can kind of see by my little stick figure, Alicia and I are pretty excited about this part. We're gonna get into a demo here in just a minute. The first thing we wanted to show was to talk about memory estimation and verifying the needs of what you may have. And the reason why this is something you want to look at is the Neo4j Graph Data Science library operates in memory. We load from the database, and then we load that into memory, and then the graph algorithms are computed on that in-memory graph. And that in the in-memory graph, we basically have an adjacency list of nodes and relationships. Now, what that means for you is that you can store node IDs, relationships, and properties. And because it runs in memory, you have to be thinking about the potential for out-of-memory errors. So you have to be able to configure that properly. One master tip, I guess, is that if you have undirected relationships, those are stored twice. So if you're trying to tune your memory, that's something to consider. And then we can also use the estimate mode to give you the different bounds, both your upper bound and your lower bound for memory consumptions. So that's a tip for you guys. And I think, Alicia, you're going to give us a quick look at what that actually looks like.
I am. So I'm pulling up my screen now. You guys should all be able to see Neo4j browser. And I have a demo database that's been loaded. This is just a retail database that we use for a lot of different demos. I have customers who are from countries. They make transactions, which contain items. And they also can just be directly connected to an item that they bought. And those items have similar relationships between each other. And they also belong in categories. So like this item is a toy, this is a kitchen item. And this is just an easy database to use to demonstrate different things, but useful to kind of just check in with what are we looking at here. So memory estimation. Really, when we talk about memory with GDS, what we're talking about is whether or not you have enough memory determines if an algorithm is going to run. Because everything's in memory, you need to have memory available to load your data into memory and to execute the algorithm. And so we've actually spent a lot of time building in functionality to make this really easy and intuitive so you can get it right. So you don't kind of do trial and error. I've done all this work and I oomed my database and it is dead now. So we've really tried to make this simple. So the first thing we can talk about is sizing fictitious graphs. So maybe I haven't loaded any data in. You've probably seen gds.graph create before. With a lot of our functions, you can actually add .estimate to the end to estimate how much memory it's going to take. And so what I'm doing here is I'm pretending I don't have a graph loaded yet. And I'm saying I want to load a graph that has 10,000 nodes, 100,000 relationships, and a node property and a relationship property. Ballpark, how much is this going to take? And you can think of this like if you're sizing a box on AWS, or you're working in the cloud and you need to figure it out, or you're just setting your database configuration. And so what this tells me is it'll take 1,700 kilobytes of memory to load that into, to load your graph. That's fine. That's not very much. If I had a really large graph, maybe I'd go back. If it says, oh, you need 3 gigs of memory, I've only allocated 2 to heap, I could go change that. Once I've got a real graph, so I do have data loaded into my database, I can actually estimate how much memory it'll take to load data in from my actual data. And this will give you a more accurate estimation. So I can say, I want to load into memory a graph that contains customers and items and just the bot relationship. So how much memory is that going to take up? And this tells me it'll take between 1,200 and 1,500 kilobytes. So this helps me narrow down exactly how much it's going to take. The other thing I can do is I can size an algorithm. So I can say, I know I'm going to run PageRank. I want to see, worst case, I'm going to run it on every node in my graph, every relationship in my graph. How much memory is that going to take? So just like before, you have your algorithm call, and then you append .estimate. And so I'm just going to run this guy, and you'll see between 2,800 and 4,000 kilobytes. Sounds good. The other thing we've done is, this is like best practice, right? You want to figure out how much memory you need, size your instance appropriately. In the event that you're like me and you don't always do that, we've added in guardrails so you can't accidentally break your database. So what I've done here is I'm going to try to call PageRank, and I'm going to try to tell it to run over all nodes in my database, all relationships, and I'm going to set concurrency, or how many threads, to 30,000. That would never run. There's a lot of overhead to try to reconcile 30,000 threads, but it doesn't let me break anything. It says procedure was blocked because the minimum estimated memory to do this, 23 gigs, exceeds the current free memory. And so we kind of keep these guardrails in place. There is a way to turn that off, so you can't accidentally shoot yourself in the foot, just starting off on the right foot. And so that's memory estimation, and I will pass it back to Amy for the next kind of cool thing.
Awesome, cool. So the next cool thing is looking at actually transforming your graph for specific needs. So a lot of times, not only do you want to get your graph into this computational format that that is really effective, and and save that for use, you probably have specific needs. Maybe you want to look at specific node types, so you can project multiple types and recognize multiple types of nodes and relationships. So you could project maybe one node type, maybe you're going to project 3 node types, and then you want to run the graph over just one of those 3. So maybe you're projecting people, cars, and bicycles, but you only want to run your algorithm on the people or whatever it might be. So being able to do that in memory is really important. You can also transform your relationship orientation. So when you load your graph, you can decide that you want to look at your graph in one direction, or maybe you want to reverse the direction of the relationships, whatever that might be. And then you can also aggregate relationships, and you might do this to either deduplicate multiple relationships that are actually the same, or what's kind of fun as well is to be able to aggregate your relationships and then weight them. So maybe you have a transaction that you're following, and you just want to follow the general transaction between bank and client, but you then want to weight it by the number of transactions that happen. So maybe it's like 50 or something like that, and then use that for your calculations. So the fun thing about being able to do that when you transform your graph is you can keep doing it as well when once it's in memory as well, to keep reshaping it. So I think Alicia has some fun stuff to show us on that one too.
Yep, let me pull it up. So you know conceptually what we're talking about. How does this look in practice? So again, just remember I've got 5 different node types, a bunch of relationships in my data, but I don't want to analyze all of these at the same time. So I'm going to just walk through a couple different ways that you can transform your graph and kind of what it looks like. And what we call this in engineering is this is the graph catalog. So this is how we manage these different in-memory graphs. And so we do this with gds.graph.create, pretty simple. And you load named graphs. And so once you've loaded a named graph, then you just call it by name and operate against it. So the first thing I want to do is we talk about native loading. And that means I'm loading based on the actual structure of my data. And I say I want to load these nodes and these relationships. So I'm going to say, I want to load items and the similar to relationship, but I want to make it undirected. I know Amy was like, warning, this is double the data. But some algorithms require undirected graphs. So I'm going to do that. And I'm going to call it items undirected. I'm also going to load a directed items graph. I'm going to call it items directed, but I want to deduplicate multiple relationships. So I'm going to load items and the similar to relationship. But what I want to do is whenever I see multiple relationships, I'm going to aggregate them into a single relationship with a count property that indicates how many parallel relationships were in my underlying data. And so I'm going to run this. It's super fast. It's using the native loaders. And now I have 2 graphs in memory. One thing that users often run into, and I'm going to kick this off running while I speak because it's a little slow, is they have a structure in their data that they have a relationship that they want to analyze that doesn't exist in the underlying graph. So here, I'm loading a graph where I want my nodes to be customers and categories. But there's no relationship between customers and categories in my transactional database. So what I can do is I can use a cipher projection to on the fly reshape my data and create a relationship in my in-memory graph that does not exist in my actual database. I don't mess anything up on the transactional side, but I have the relationship I need in memory. So what I'm doing is I'm saying match customers and categories, and that's how I get my nodes. And then I'm using a cipher query to say, find me customers who make transactions that contain items that are in categories. And I'm going to connect the customer and the category in that to create my source and target nodes. So my in-memory graph is something that doesn't exist in my underlying data. And so that took a while. It was a 4-hop query, but it's loaded now. And I've got my customer similarity graph. And it's told me when I did that, I loaded 4,300 nodes and, oh dear, like 36 million relationships. So that's why it was slow. So another
Lisa,
thing,
and I got to say, what I really like about this, what I find it really cool is that you can, you've created these relationship and you haven't touched your original data. Like you're not mucking with your pure original data set.
Yep, I'm not ruining anything. I'm just exploring kind of in the in-memory workspace. There's another thing that we don't talk about a lot, but there's special star syntax. So if I do, for some reason, want to load everything that I have into memory, instead of naming nodes and relationships, I can just pass in star and star, and I'm calling this my kitchen sink graph. And this will really quickly just put everything in my database into memory. And so I've loaded now 4 different shapes of data. we have this function called graph list that actually keeps track of all of this stuff I've been putting into memory. So I've got 4 different graphs and I can see each of their names. The customer similarity graph by category, items directed, deduplicated, undirected, kitchen sink. I can see how much memory they're taking. So you can see that my kitchen sink graph is by far the largest, or no, this guy's the largest because he has 36 million relationships. I can see this one as a cipher projection. So I see the queries that I used to create it in case I'm wondering, like, what is this? Where did it come from? And I can see how many nodes and relationships are in each one of these. So it's pretty easy to track. I've been layering, I've been creating new subsets, new graphs, new projections. I can keep track of what they are and what's in them. And remember, we want to manage our memory. When I'm done, I don't want to leave these hanging around. So I just go in and I use graph.drop, and I have cleaned up after myself. And so it's done. So that is like super fast. How do you transform your graph into a lot of different shapes? Deduplication, changing directions, cipher projections. There's so much you can do there. And I will pass it back to Amy and stop sharing for the next cool thing.
Awesome, great. And I was going to say, if it was only that easy to clean up after ourselves. So anyhow, next area is security. Now you might think, oh, that's not very exciting, but if you think about what security allows you to do, it is kind of exciting. So the GDS library now respects whatever access controls you've applied to the underlying database. So if you're using a role-based access control in your Neo4j database, which is available in the Enterprise Edition, there are things you can do to tune the security access. So in this example, you might have a customer service person and a doctor, and they may have access to the same graph, but you want them to be able to see different things. So you might have the customer person, the service person, being able to look at the patient information, their billing address, their phone number, that type of information. But you wouldn't want them to actually see health information. But you would want the doctor. So letting people see that different information. And an example here is just an algorithm, K shortest path. So looking at the multiple shortest path. I think we're looking at, we're just doing one, K shortest one path. So we're just looking at a path, looking at shortest path between 2 points, and using the same exact algorithm, we have 2 different views depending on the rights you have. So really quite powerful, because we can go down to the node relationship level and give people different access to that. So Alicia, can you show us what that looks like?
I can. So let me share my screen again. This one is not as exciting to look at because we're just going to look at some roles. But what I've done is, so in Amy's example, you have doctors. Maybe you don't want people seeing PII. Before this demo, I added a role to my database called analyst. And I guess I shouldn't be showing you guys the password of the analyst, but it doesn't matter. This is a demo. An analyst is a reader role. So right now I'm logged in as the admin. So I have full control over the database. I created the analyst role, and I did 2 things. I said the analyst role cannot traverse the from relationship in my source data. So I have customers, and they have a from relationship that ties them to their address. And maybe I don't want my analysts reading people's PII. So I'm going to say analyst cannot see the from relationship. And then I'm going to say I don't want them to read the quantity or price data that are on the contains relationship. So every transaction contains items. On that relationship, I have a price and a quantity. And for whatever reason, maybe I don't want my analysts to be seeing how much people paid. I'm going to deny their ability to read that. And so what this means is they can access the database. There's just certain parts they can't. So me as admin, so I'm not going to rerun this. This has already been run. I'm admin right now. I want to run an algorithm. So I'm going to use that ** syntax I talked about earlier, just to be super fast. And I'm going to create a graph in memory, and I'm going to say I want to load that quantity property when it's available on a relationship. So I want to use that as a weight for something. And what this will do is, as admin, I create my in-memory graph. If quantity is defined, it'll put that value on the relationship. If it's not, it'll just have a null. And so I've loaded all nodes, all relationships, and the quantity data. And I can just take a peek. What have I loaded? I can see I've got 28,000 nodes, a little over 1 million relationships. Now I can run PageRank. And so I'm going to run PageRank on this data, and it's just going to show me what's the highest PageRank and what's the node ID that's associated with that. And so I see that node 1006 has a PageRank of 25. And this is using all of the relationships in my graph and that quantity value as a weight. Now I'm actually going to switch over. I've logged in a separate window as the analyst role. And so let me maximize this. So over here, I'm logged in as the analyst. I'm going to try to do exactly the same thing. So I'm going to create a graph. I'm not going to call it kitchen sink admin because I'm analyst now. And we're going to run it. And so I'm loading this into memory. And I'm going to just, as that goes, I can't see the from relationship here anymore. It's gone. So the country is just an orphan node. And I can see actually, first difference, I've loaded fewer relationships into memory because I deleted those. Now I'm going to go back and I'm going to try to run. So I'm going to try to run PageRank on this graph that I've just created. I'm going to change admin for analyst. And I'm going to, again, let's say I'm just copying queries from somewhere. I'm going to try to run it with relationship weight property quantity. And let's just see what I get. So what this is going to do is this is the PageRank based on the data I can see. I can't see certain relationships, and I actually don't have access to the quantity property. So it's always just going to be null. And I get totally different PageRank scores. So now the highest PageRank is node 2600 with a PageRank of 3.79. And so this is because there are no weights, and I can't see some of the relationships. So where this is really important is if you don't want GDS to be the security hole, right? If you're running GDS with RBAC as of 1.3, Enterprise Edition GDS users respect all of the security controls that you've applied. So if your analyst shouldn't be reading people's PII, it's not available. So you can hide nodes, you can hide relationships, and then that's all reflected in your in-memory graph. And so that is the security demo, and I'll pass it back to Amy.
Awesome, great, thank you. So another area that's kind of exciting is, and there's just a lot to it, is tuning the algorithms and using different parameters. So we're just going to talk about a couple here. We've got the parameters detailed in the docs if you want to dig into any of them. But there's a couple that we've added that are really helpful. One is seeding. So some of the algorithms are naturally not deterministic, which means the results can vary depending on what the start node is and how ties are broken. So what seeding does, especially for these community detection algorithms that tend to be non-deterministic, is it allows you to add values that are appropriate at the very beginning of the algorithm run. And then you can also set how you want to break ties as well. So, and what that does is it allows you to have consistent results, and for a production environment, that's pretty important. And you can basically set these initial values for things that are appropriate for the labels. The other thing you can do with seeding is you can also use that seed property for subsequent algorithm runs, and that can help you look at delta, more of a delta calculation in certain scenarios. So important to play with it, especially if you need those consistent results, or if you're not getting consistent results, definitely take a look at that. The other thing is concurrency. So it exists. That's one of the big things is definitely look at the concurrency. So the algorithms are parallelized. We talked about that so that they can run super fast and can run at scale. They take advantage of multiple threads. The concurrency default is 4. So if you are using Community Edition, that's what it will be set at. It is unlimited for the Enterprise Edition. I don't know if you can get to, what did you set at, 30,000 concurrency? That would be fun. But it is unlimited for Enterprise, and it needs to be configured. So if you're an Enterprise customer and you're just going by the default, definitely look at that setting and up it to what's appropriate for what you're trying to do. The other area is just thresholds and tolerances. So a lot of the algorithms have a lot of different thresholds that you can set. You might set to a similarity cutoff or degree cutoff. So, and what that'll do is that'll help you tune what you might want to base your algorithm on, or what your results will be. So for example, you might want to say, I want to run this algorithm only on starting with nodes that have a higher degree centrality, because those are more likely to be included in my results in the first place, which will help you balance performance and accuracy needs. Another setting or parameter would be things like tolerances. So you might want to set kind of a minimum change score. So for example, PageRank, you might say, hey, after the scores stop changing within 0.01% or whatever the change tolerance you want, that I want to go ahead and complete. And you can set that alongside of things like max iteration. And these things, again, allow you to kind of tune for balance, accuracy, and performance. There are some algorithms like PageRank, if you set nothing, no tolerance, and no max iteration, theoretically, it could run forever. We have defaults, but you want to definitely tune those as well. So, Alicia, why don't you show us a little bit of the parameters tuning?
Sounds good. Let me resume sharing. And so I'm going to just walk through an example with label propagation. I could literally spend like 6 hours talking about parameters. There's a lot of like really cool stuff hidden in the details. I was going to be like, you could read the docs for fun, but then I remembered most people don't do that. So I'm going to walk through some examples and point some cool stuff out. So Amy talked about seeding. I'm going to run through an example where I have a graph. I'm going to run label propagation once. I'm going to add some more data, and I'm going to use the seeds so that I don't recalculate. So what I want to do is, we know all about graph creation. I'm going to create my item graph, and it's going to be an undirected graph that has a similar relationship. And what I want to do is, the first time I run it, I'm going to run label propagation in write mode. And I'm going to just point out, usually we would just, for a demo, we'd say label propagation dot write, and we would just pass it the items graph and set write property, because those are the ones you have to set. I'm doing a couple other things here. So these are some of those pesky parameters that we hide in the background. Max iterations is how long do I want this to run? And I'm going to set max iterations to 1. So that means I'm going to only do 1 step of label propagation. This is actually kind of like a neat hack. So one thing I've seen people do is, if they have a value on a node and they just want to assign that value to all the neighbors of that node, they'll run LPA with iterations 1. I'm going to set concurrency to 8 because I'm running Enterprise Edition. And I'm actually going to tell this algorithm that I want consecutive community IDs. So this is like something we added in, I think in 1.2, so that if you're running community detection algorithms, they're stochastic, they assign community IDs. You might get, community 4, 23, and 4012. And we had a lot of users saying, why can't they be called 1, 2, and 3 if there's no numbers in between? And we actually added in, well, now you can make them consecutive. So I'm going to just run this and get my initial run of the values for label propagation. I can see all of those run. And then I'm going to add nodes to my graph. So I'm very familiar with this data set. I know there's an item called space owls. And I want to add some other kinds of owls to my graph. I'm going to add a sea owl and a land owl and a potato owl. And they're going to be similar to my space owl. And for this example, I'm just adding a small delta. But you could think of this, if you're a company, every day new purchases happen, right? So I've run communities on my data today. Between today and tomorrow, I get 10% new data. It's been added into my graph. And then I need to rerun label propagation. So I'm going to add my new owls to my graph. And I'm going to load that new graph into memory. And I'm going to just take a peek at my owls that I put in here. So space owl was that anchor one that I added my new owls to. And I can see here's space owl. It's got label LPA community 2838. And it's connected to sea owl, potato owl, fire owl. And those don't have any communities. They're new. So what I want to do now is I'm going to rerun label propagation, but I'm going to tell it my seed property is the LPA community. I'm going to write to LPA community as well, so I'm just going to update it. And this time I'm going to say it can iterate 10 times. And all I'm doing is just using those seeds. Space Owl should keep its community, and I'm seeding the new data. So let's have this run. Super fast. So this actually only took 2 iterations to converge. But let's go back and check our Space Owl and its neighbors. And now we can see, well, Space Owl is still 2838. It kept its community ID. I didn't change everything. But now Fire Owl is in the same community as Space Owl, and so is Forest Owl. So they've now been updated with those seats. So this is just kind of a toy example, but you can start to see there's a lot of stuff you can tweak to do things like seeding or get consistent results or kind of change what your outcome might be. So this is mostly just a pointer. Check out the docs. There's a lot of cool stuff in there. And I will pass it back to Amy.
Great, thank you. And I think the webinar host and I would like to know if you ran a similarity algorithm on Potato Owl, if it would show an overlap with Potato Head. So
wow.
You never know. All right, the next fun thing, the next tip is about versioning and graph versioning. You can use .export to do that, and that basically exports and contains your in-memory graph, your nodes, your relationships, your properties, everything that was in there. It's super fast, and I'll let Alicia tell you how she accidentally found out it was super fast. So you can create millions of relationships, exports in seconds. You basically get a snapshot of everything you've done in that in-memory graph, and it can be quicker than writing back to the database, and it also can be used to snapshot and kind of version your work as well. So if you think about testing out stuff, playing around with some parameters, wanting to export to a new graph, and then a new graph database, and then you can do whatever you want with that separately without touching your original, and do that multiple times and just kind of have that little bit of a versioning of the different graphs you played with. So Alicia, why don't you show us, and definitely please tell us how you accidentally figured out it was so fast.
I'm glad this is a story that we're going to keep talking about. When you run similarity algorithms, there are some parameters you should set, kind of on the last point. And one of those is top K and top N, which is kind of how many similar relationships should I create? And I wasn't really paying attention, and I didn't set them. So it just created as many as there were. And then I just mutated my in-memory graph. And then I was like, cool, that worked. Let me do graph export. Exported it for a demo. And then when I went and looked at the graph I'd exported, I was like, oh, dear Lord, I have created a graph with like 50 million relationships in it. Well, that was fast. So that was like a fun way of figuring out what I've done. So for this, what I'm going to do is, this does not have millions of relationships. I'm going to export my Space Owl similarity graph. Let's say I was working today and I want to just keep track of it for next time around. So I'm going to call GDS graph.list, and I'm going to just check out my graph in memory. And so I've still got that items graph. It's only got 2,900 relationships. It's not a crazy one. What I'm going to do here is, I have that in memory graph. I want to snapshot it. So I'm going to save it to disk so that if I come back a week from now and I say, what data was I analyzing on, August 12th? I can go back to it and I can see exactly what I analyzed and exactly what I did. So super simple. All you're going to do is call gds.graph.export. You give it the in-memory graph you're trying to export, and you give it a database name. And this is going to just create a new database called August 12th. So it's using admin export. And I have an error because I passed an empty query. So running GDS graph export, now I can go see my new database. So I'm going to use system. And these are some of those 4.0 multi-database features if you haven't seen this before. So now I'm using the system database, and I can activate the database I just exported. So I exported August 12th. The store files are there. All I need to do is type create database August 12th to see it. Now I have a database. I can do show databases. And this will show me all of the databases I've created. And you can see I've been practicing. And now I can actually go and use that version database. So use August 12th. And now I am using the August 12th database. And if I look at just what I have here, remember, I just had that item similarity relationship. So this is what I had in memory. I could do the star projection to pull it all in at once. And I can just take a peek and I can see here are those similar to relationships we were looking at before. And all I've exported is just the data I was analyzing. And so now I have it and I can save it, and it's just available for next time. So I can every day just serialize to disk exactly what I did and keep track of it. And it's also a really good way of debugging. If you're like, I'm not quite sure what I did in my in-memory graph, I used a cipher projection and I'm not sure if it did what I expected. Graph export is a great way of just kind of introspecting that. And so, yeah, that is graph versioning. I'll pass it back to Amy.
Very cool. All right, up next, number 6, which is a fun one. So play with our experimental features. So we have 3 tiers of algorithms available in the library. We have a production quality tier that the algorithms are fully tested in regards to stability and large scale. They're also very robustly documented. We have a beta tier where things are about ready to get to production quality, and they'll be coming shortly. Maybe they need a little documentation, that sort of a thing. And you can call those by adding in .beta. So it's GDS, call GDS.beta, and then whatever the algorithm is. And then we have a fun alpha tier. And this is where a lot of our engineers get to play around and try new things out. And it means that it's experimental. We might change things later. It might be removed later. And you can use the alpha domain namespace for that. Now, you might say, well, hey, it's going to change. Why would I want to touch it? Well, a couple things is you get early access to things that may become production quality later. You get to give us feedback, so we really appreciate that, and I think that's actually why a lot of the algorithms and what we're doing are just so solid, and that we're very happy that we can add in these functionalities like seeding, which actually came from customer feedback. And you can help us drive the direction of things as well. If you see something in there, you feel like, hey, we have to have it, let us know. If you see things in there that aren't working the way you expect, definitely let us know. The other thing is it's just kind of a cool area to play with. And so one of the things that we've added to the alpha space lately that is really cool is graph embeddings. If you're not familiar with graph embeddings, there's a lot of information out there that you can read in more detail. We do have some information on our docs as well as our developer page on them. But basically, you're trying to translate your graph or portions of your graph into a fixed length vector. And so it's a tighter, lower dimensional representation of what you have in your graph. You get to preserve the structure of your graph, and you can use that for machine learning or similarity comparison or other functions. And so we've added 3 proof of concepts for node embeddings. We've got random projection, Node2Vec, and GraphSage. Random projection is really fast. It doesn't take into account node properties, and it uses linear algebra. It's very similar to the fast RP algorithm out there that you guys may have seen. We've also got Node2Vec, which is probably the most well-known. I would say most well-known graph embedding out there. It tends to not be as fast as the random projections, and it doesn't include the node properties. GraphSage is a little bit slower, but it also lets you add in node properties, which is really cool, and it has some nice functionality in that area. So, Alicia, do you have anything to show us on the graph embeddings, or is it too new to actually even look at?
Oh, I can show you.
Awesome.
So let me resume my screen share.
Okay.
Awesome. So I'm gonna demo Node2Vec. So graph embedding, what this is gonna do is it's gonna take every node in your graph and it's gonna give you a bunch of numbers that describe that node in the context of the topology of the whole graph. And it works by, for every node, you take a set number of random walks across the graph, and then you build up kind of context. So you have all these random walks that describe your node's position in the general graph. And those random walks are passed through a neural network, single layer neural network, to train a model to predict, given a node, what's the next node. And the embedding itself is just the hidden layer, the weights that neural network learns to make that prediction. And I could talk about this all day, but this is not a presentation just on embedding. So we're just going to give you a sneak peek. So it's gds.alpha.node2vec. And because it's an alpha, it only supports stream and write. So there's no stats, there's no estimate, there's no mutate. I'm going to pass it in that same items graph that we've been working on. And I'm going to tell it I want an embedding size of 10, which means I want 10 numbers to represent each of my nodes. I'm going to tell it I would like a walk length of 10. So from every node, I want you to take a random walk of length 10. And in-out factor just kind of controls how biased that random walk is. Basically, you can control whether your random walks go far out in the graph or if they stay local. And depending on how you tweak that parameter, you'll learn different aspects of the structure in your embedding. Basically, if you keep your graph local, so your in-out factor is above 1, you're going to basically learn a representation that has nodes that are near each other in the graph having very similar embeddings. If you set it so that it instead is going far afield in the graph, kind of a depth-first search, what you're going to learn instead is you're going to learn structural roles. So you'll have nodes that have very similar structural roles being very similar to each other. So I'm going to run this. This is running on 28,000 items. So it's not a very small graph, but it's pretty fast. And what this will give me is it gives me for each node, here's the embedding. So when we say fixed length vector, we mean a bunch of numbers. So I've run this, and usually what I'm doing here is I'm just checking, do the embeddings look different? If you haven't tuned it well, or if you've done something funky, you'll get like all of your embeddings kind of look the same. That's a tip. Go back and change your parameters. I'm happy with this. So what I'm going to do now is I'm going to just write it to the graph so I can save my results because there's no mutate mode yet. And now every node in my graph has its embedding saved to it. And now that I have that embedding, usually we see users putting that into like a machine learning pipeline or exporting it as a feature. I think of embeddings as kind of like one feature to rule them all. What I'm going to do, just so we stay in Neo4j land, is I'm going to run cosine similarity. So I'm going to say, for all of my nodes, all of my items, I want to take the embeddings and I want to do cosine similarity. So how similar are nodes to each other based on their embeddings? And I'm just going to return, I'm not going to create a new relationship. I'm just going to stream these results out. Notice that cosine is another alpha algorithm. So we're using lots of experimental stuff here. And I'm just going to see, what do I get that's similar? And so this is going to run not too slow. I'm comparing, I guess, 3,800 nodes to each other. And now based on those embeddings, what I found is these items are similar to each other. And this actually looks pretty good for just kind of running this randomly. I can see that jumbo bag with doily patterns is similar to jumbo bag red retro spot. Or, you know, these different colors of mugs are similar to each other. So I'm able to detect the items that are very similar to each other without kind of building any complicated model. All I'm doing is training an embedding to represent them and calculating the similarity of those embeddings. So sneak peek, but get excited and give us feedback.
Awesome. Thank you, Alicia. You've got the best data sets out there. That's the most fun data sets. The last item that we're going to talk about, or the last tip, I should say, is really using your own algorithms and then implementing them with the Pregel API. So we have a mid-level Java API for implementing your own parallel graph algorithms. It requires, because we've done that with the API, you don't have to know as much about the GDS internals or the Neo4j internals to actually implement your own algorithms. We looked at implementing in a way that could be as stable as possible. So that's kind of the approach we took. And I will say, just so I don't forget, that we will have a under the hood session on the Pregel API coming soon. So you'll probably see that or let us know if you're interested in that. If you're not familiar with with Pregel itself, it's basically a BSP model. And so there's a computation phase that goes on where you try to parallelize all your compute. And, you know, and I like this visual because you can see not everything completes at the same time, as it never does. And then you have this bulk communication and synchronization phase, and you continue to iterate on that process. So Pregel is exciting for a lot of people, especially if you've already written some algorithms, maybe you're using them somewhere else, and you now want to implement them in Neo4j. If you've used Pregel, it's much easier to just bring over those algorithms. So let's take a quick sneak peek at that.
So now, instead of showing you a browser, I'm actually showing you IntelliJ, which is a Java design, Java IDE. And this is actually the source code that's behind GDS. So GDS is written in Java. It's a plugin. What I'm showing you is actually, this is our source code. And in our source code, we include the Pregel API. So you can get this on our GitHub. It's on Maven Central. You just copy over our code. And this is a Pregel implementation of PageRank. So the reason I haven't zoomed in is I want you to see how short the implementation is. So what we've done is we've created all the building blocks for Pregel. How do you pass a message? How do you start? How do you stop? How do you store data on nodes? All you have to do is put those pieces together. So we've got a bunch of examples in our repo. We've got label propagation, PageRank, single source shortest path. We have those so you can kind of compare and contrast between the Graph API that I use and my team uses for implementation, which is our kind of really low-level last mile performance code. That's how we can get node to vec to finish in time to run a demo. This is kind of a step up. You don't have to know all of the internals. We give you the building blocks, and the performance isn't bad. And so if I want to implement PageRank, all I'm doing is defining PageRank. I have my PageRank Pregel class, and I'm just combining these building blocks of like start my initial super step, get a node value. How do I pass values? I just have my little formula for damping factor and jump probability. And then I just use these existing classes that have already been built in, set node values, send messages. So it's really pretty plug and play. And if you've ever used Pregel, Pregel is available in GraphX and GraphFrames. It's available in a lot of different languages. Basically, it's the same framework. If you have an algorithm and you're like, wow, I wish that was in GDS, you don't have to learn to be an excellent Java programmer. I am not an excellent Java programmer. If you just Google name of algorithm, Pregel, you'll basically find the pseudocode, and it's just a matter of kind of putting these steps together. So this is a sneak peek. We're going to have some of the engineers demo this later on, but check it out. Look at the code, give us feedback. We're really excited to be opening this up as of 1.3 to let folks, build their own algos.
Very cool. So I didn't tell Alicia, but I added a couple slides here to the end of the document because I listening to Alicia talk, and if anybody's been on these other sessions, talking about how it can be very complicated to perform data science, and in particular graph data science, where you might not have as many resources out there. One of the things that that Alicia talks a lot about is going from how do you shape your data, and hopefully you can see that we've improved that with that transformation. Picking the right algorithms and having documentation for that. Learning syntax, like you might pick a great library, but now you've got to learn the syntax for that. You've got to reshape your data, and then once you've reshaped it, you've got to get it into production. So I'm sure any of your data scientists out there understand that this can be very complicated. I added this because if you listen to them speak and talk about it, these are the faces that they make as they talk along the path of what they have to go to, going from I'm not sure what to do to being very unhappy about trying to get something in production. And I just wanted to, I hope from what you've seen today, and I just wanted to emphasize that Neo4j is trying to simplify the experience, trying to democratize graph data science, so you don't have to model your data. It's already in a graph itself if it's in Neo4j. We've got a lot of documentation. I know we refer a lot to the docs, but we do love our docs, trying to get as much information in there as possible. The syntax is standardized, it's simplified. We've done a lot to standardize the API, and we actually do that reshaping for you of the data to go from the graph storage to the computational graph. And then you don't have to do something new to get it in production, because you can write or export back to Neo4j and then move your model into production. So just wanted to emphasize some of the ways that we're trying to do to make the experience as seamless and as simplified as possible. So anything else, Alicia? Oh, and fun. Yeah, see the little heart eyes. Definitely very fun. Anything else before we move to questions, Alicia?
No, I'm just really glad that all of you have joined and that we get to tell you guys about something that, you know, doesn't get as much attention. Like mostly we're like, there are so many algorithms, let's tell you what they do. But this is kind of all the tips and tricks to really get stuff up and running in production.
Great. Wonderful. Well, Marilee, do we have some questions do we have time for questions, I guess, that are out there?
Well, we are coming to the top of the hour, but we do have tons of questions. So I want to kind of sort through some of these and pick some that can appeal to the broadest audience. And one of them, and this is an important one, you mentioned it earlier in the presentation, but someone asked, actually many people asked, what if I have feedback? You talked about providing feedback. How do people provide feedback?
So the best way to give us feedback is to go on our GitHub. And I guess we can paste the link for you guys in the chat. We have a public GitHub. You can file an issue. If you have feedback on something that works or doesn't work, you can also post on the community forum. And we're pretty responsive there. And there's also user Slack. So there's many different ways to kind of get at us, or, you know, just send us an email. We're excited to hear what's working, what's not working. And your feedback is how we make this a better product.
Excellent, thank you. So here's one, and I've seen this one before too in other sessions as well. What's the difference between Community Edition and Enterprise Edition?
So Community Edition, that's the one you get. You just download it from the download center, or it's in desktop. That has all the algorithms, but you're limited to a total maximum of 4 cores. And there's some features that you don't have access to, like the RBAC that we demoed today. That's only available in GDS Enterprise Edition. So otherwise, GDS won't pay any attention to your security. There's also, when you have Enterprise Edition, you get 24/7 support and kind of all of that good stuff.
Great, thank you. Let's see, we have time for about one more. How about where can I get access to the newest release of GDS?
Check out the Download Center, neo4j.com/download center. That's where the releases are up. They're also on our GitHub under the releases page. And then also in desktop. We don't actually put our preview releases in desktop. So whenever we have a new release that's out, we have a 2-week preview phase. Those are only going to be available on our GitHub and the Download Center. But once something is GA, it's just available in desktop as a plugin that you can download at simple click of a button.
Great. And I'd like to just call out a few of the resources here. So if you're not sure where to find something or where to get started, you can really just simply go to the main webpage, neo4j.com/graph data science. I try to link things to here as actively as they come up. So that's a good place to just start. Like, I'm not sure where to start. You can find the sandbox links from there. You can find the download center from there, things like that. The developer guides is also an excellent place to go as well. So a little more explanation, a little more technical explanation, and links to material. So those two are really great ones to just get started, and then kind of find what you need from there as well.
Great, thank you, Amy, for that additional explanation of the resources. We're about at time. We're at the top of the hour. So I just want to thank Alicia. Thank you, Amy. That was an excellent Insiders Tips and Tricks presentation. And thank you to our audience for joining us today. Keep an eye out on your inbox. We will be sending a link to the recorded presentation. You can share with your colleagues. So with that, I'm going to wish everyone a great day, and we'll catch you on our next webinar. Thanks so much.
Thank you. Bye.
Thank you.